morning. Thank you for coming in this cold winter morning. I didn't expect so many to turn up, but thank you for doing that. So today we are going to start the last topic that we are going to have for structures 1, deflection of beams. So maybe we'll be able to finish the theoretical aspect of it this week, and then we have got 2 weeks to go through your queries as well as solving more problems, for example. So from problems from the tutorial sheets as well as any other problems related to understanding that you may have. So the final topic is about deflection of beams. So we started off with equilibrium, if you remember, and then use the equilibrium principles to analyze trusses and internal forces in trusses, axial forces, compression or tension. Then we moved on to the beams and how the beam stresses would be developed, and also before that we looked at briefly material properties, how the bending stresses develop, shear stresses develop, axial stresses develop as well. So we'll probably do few more examples on the stress side, which is in the learning module. In this week's one, there are 2 tutorial sheets there. So 2 tutorial sheets there in learning module for this week. One is for stresses and finally one for beam deflection. So we'll have a look at that, look at those problems later. But the final topic is how much a beam deflects. Now why it is necessary? Now it is necessary to primarily check whether your structure is serviceable. For example, if you step onto a bridge and bridge starts to deflect too much, then it may be highly inconvenient, like imagine walking on a rope bridge, for example, to cross a river. So having too much deflections may not be ideal. It can lead to other problems. Maybe things will crack if it deflects too much. It may not fail completely, may not collapse completely, but it may crack. Or it may vibrate more. If it is, again, giving the example of the rope bridge, if it vibrates more, then deflection is an issue that we need to deal with. Or maybe you are an aircraft and you see the wings are deflecting and vibrating with a high amplitude. So that may not give, it may not fail, but it doesn't give confidence to the passengers. So deflections is important, and we need to be certain about, given this is the load, how much it is going to deflect. Now there is a way to calculate deflection for trusses, which we are not going to go through. You will do it in second year, and for this one we'll just do the deflection of beams. I may tell you how to do it for the trusses though later on next week if I have got time, but that's not in the syllabus. So let's start with deflection of beam. So how do we calculate deflection of beam? Now a beam with my model foam beam, if I put a bending moment to it, then it deflects. And we have assumed this sort of a hogging moment so that it is deflecting upwards as positive. So we need to know how much it deflects. Now bending causes a beam to curve. Now we can measure the curvature at each point, and then the curvature would be, from the curvature we can find out how much would be the deflection. Now the way to do it, of course, we have to recourse to maths here. So the curvature and something called radius of curvature, they are inversely proportional. So if for a beam or any line really, the curvature is given by the Greek letter kappa, then radius of curvature is 1 over r. So what we mean is, if we have got a circle of radius r, so if this circle has got a radius r, its curvature is given by kappa is 1 over r. Now you can also appreciate, if that is the case, then if something is a straight line, then we know curvature in this case is 0, because straight line means no curvature. So its radius of curvature is 1 over kappa, which is infinite. So which you can say. So how do we calculate curvature? Now of course from the curve, so if you have got a certain curve, you want to find its curvature. The way you do it, say, let's say you have got a curve like this. So you find out two perpendiculars, for example, at nearby points. So you take a point and you find a normal to it or a perpendicular to it. And then you find another nearby point and find a perpendicular, draw a perpendicular to it, or normal in this case. So where they would meet, that's the center of curvature. So this is the center of curvature. And from that center of curvature, you can find whatever that radius is, and 1 over r is the radius of curvature. Now this curvature is intrinsically related with bending. So the bending introduces curvature. So if you have got more bending, you will get more curvature. In fact, that is what we saw in previous bending stress calculation. Let me find out that particular note, or I can show you from previous weeks over here. So part 5. So this formula, again, we looked at here, and we introduced you this concept of the curvature with the radius of curvature r here, and this particular formula that we came up with, if I can make it bigger, that moment over second, bending moment over second moment of area is sigma over y is E over r. Now forget about this second bit here for the time being, because that relates to the stress. Consider the first and the last one. M over I is equal to E over r. So if you know moment that you are applying at one cross section or bending moment there, and then you could get, so there is a relationship between moment and curvature. So 1 over r is curvature in this case. So you apply more moment, it will curve to a higher curvature. So if in this case it's a flat to start with, so curvature is 0. So it's a flat line. So that means radius of curvature is infinite. What do I mean by radius of curvature? So you draw two perpendicular lines through the midpoint, and they will probably meet at infinity. So radius of curvature is infinity. So you have got curvature as 0. So that makes sense that straight line has got no curvature. It's straight as opposed to curved. Now if you apply moment to it, then it starts to get curved. So it has got certain radius of curvature, and radius is fairly big now. Now if I apply more moment, it bends to a tighter circle. So radius of curvature is getting smaller, or in other words, curvature is getting bigger. So you apply further moment, then curvature is getting higher and higher. So more moment you apply, more curvature you get. Now, how do we get the deflection from here? Now, we have to recourse to math at this point. Now, if you have got a curve with, if you have got a curve, say, versus x versus y, a generic curve like this. So, if you do x versus y, so any point, or rather it is drawn slightly down. So, if you have got a curve x versus y, and then at any point you can draw the gradient dy dx, and rate of change of this gradient is the curvature. That's approximately. But you can draw the curvature in this way. You draw a perpendicular there, a perpendicular there. For example, wherever they meet, that's your curvature, as you said. Now, what is this expression of curvature? Curvature is 1 over r. Mathematically, this is the expressions. It's quite scary looking. That curvature is d2y dx2 divided by 1 plus dy dx square over 3 over 2. Now, we are saying that is related to the moment. Now, solving this, now you have started probably differential equations in maths, have you? Not yet. You have?
Ordinary differential equations?
Exactly. Yes. Okay. So, solving, can you solve this one? It's horrendously difficult to solve these particular differential equations for certain values of m. Now, as I keep on saying, engineers do take approximation. They look at this expression and they say, what happens if I have got a small deflection, or dy dx is small? So, if I have got a beam and it doesn't deflect much, for example, it's like this is the deflection, then the slope, maximum slope is small. Let's say slope is 1 over 10 maximum. Then these equations would give you kappa is 1.015 d2y dx2. So, you can approximate kappa or the curvature as d2y dx2, and this is what we are going to use. Now, the curvature of a beam can be expressed as rate of change of the gradient. So, the gradient is dy dx and rate of change of gradient is d2y dx2. That's related to kappa. Now, of course, is the curvature. Now, moment is equal to EI times the curvature. So, EI times the curvature from the previous expressions. So, if you look at here, moment is EI times 1 over r. So, EI times curvature is the moment here. So, you can say this is moment is equal to EI times d2y dx2. Now, this is an ordinary second order differential equation. So, what is y? Y is the deflection of the curve. So, at any point x, this is y. So, if this is x, that is y. Y is the deflection that we are interested in. So, if I know moment or the distribution of the moment along the beam, and I know E, which is the property of the material that the beam is made of, if I know I, which is the second moment of area, property of the cross section, whether it's a rectangle, square, circular, angled, or whatever, I can find I. Then from these differential equations, I can find out the slope, which is dy dx, as well as the deflection. Okay, let's try that. Let's try that with an example. And I'm going through the notes exactly the same way that I'm explaining to you. So let's. So this is another description of that. So sign convention we will be using, and different, as I said, different books always have different sign convention. But for this class, I'll take positive deflection is downward. Now, why do we do that? Normally, you take positive deflection as upward, but normally the loads that we have on structures are downward due to gravity. So, it makes sense to have the deflections due to positive load as positive as well. So usually many books will take positive deflection as downward. Now what is positive curvature? Now if it is bent in such a way that the center of curvature to the positive deflection one, then that is positive curvature. So I'll give you two examples. So if your beam is bent, like this, so you apply a moment and beam is bent that way, so the center of curvature is in this direction, which is in the positive direction. So this is positive curvature. So this is positive curvature. And if the beam, so moment makes this is positive moment, and this is also positive moment from our sign convention, so that is positive curvature. Now if the beam is bent that way, for example, due to moment in the opposite direction, so the center of curvature would be in the negative y direction. So this is negative curvature. So this is negative curvature. Okay. So if it is so this is also called sagging bending moment, and the other one is called, sometimes people use this term, sagging and hogging as well. So this is hogging. I don't know what the origin of the term, but hogging, I don't know what it means, but it's going upwards. Okay.
So negative curvatures are caused by sagging bending moments.
Yeah.
Positive curvatures by hugging bending moments.
Yes, and that is purely because the way we have chosen our moment direction. Always remember, positive moment creates positive curvature for our lecture, our course. Some books would have this would be with a negative sign. Some books would have m equal to minus ei d2i dx2. Possibly they take bending moment as sagging as positive, so they get a different sign. Some book would have y going upwards. So you'll find, if you pick up 4 books, you'll probably find any combinations of those. And as a result, this could be plus or minus. Some books would have y positive, so this could be negative in that case. Some books would have sagging bending moment as positive, so then that would have, and this is y downwards, so it could be negative. Some would have y upwards as well as sagging upwards, so then that would be plus as well. So the way to test all of this is whether positive moment produces positive curvature or not. If it does, then that's a plus sign. Now, what is a positive curvature? Now, if it is bent due to the positive moment, then if the center of curvature is in the positive deflection one. For example, if I give you, say, you are picking up a book which has got deflection upward as positive and bending moment sagging is positive. So this is a positive moment. So this is a positive moment. So what you have to do is you have to think, if I apply positive moment, where the direction of the curvature is. So that is positive side. So that is a positive curvature. So m would be ei d2y dx2. So with a plus sign. If in this case it was y was downward, then that would be with a negative sign. So make sure that you use you look at that for different books that if you are referring to. Now for us, it's I have done the sign convention so that everything is plus positive. V dv dx is w, m is dv dm dx is plus v. Similarly, m is plus ey dy d2y dx2. So let's find out how we can find the deflections in these cases. So I'm going through these notes. So let's say we have got a beam which is under UDL, and UDL intensity is W per unit length. So W per unit length. So that So that means total load on the beam would be W times L over 2. So that would be the total load. Thank you. So the reaction would be WL over 2. Total load is WL. That's it. Thank you. Thank you. So the reaction force is, in this case, is half of that load because it's symmetric, WL over 2. Thank you. So how do we use this expression to calculate deflections? So we'll be using these expressions. So what we need is to find moment at a generic distance, at an arbitrary distance x. So if you take moment at a distance x, so let me take a different sign. So if I take a distance x from the left hand side, I want to find what is the moment at that location. So I want to find moment at that location. So I will consider this free body diagram. So the free body diagram would be, in my case, I will have this beam of length x, and so the length is x, and it has got one end, it has got a reaction force WL over 2, and it is subjected by a load which is W per unit length. So W per unit length is load, and then I have got a shear force which will act at that point, and a bending moment which will act in this direction. So this moment I am interested in. So the moment at a distance x, this is what I am interested in. So how can I find this moment? Now of course I can take equilibrium equations for this one. So I could say moment due to three forces. If I take moment of this beam due to WL over 2, so that will create a clockwise moment. So I could say WL over 2 times x, moment due to this. That's a clockwise moment, so positive. What about the moment due to the load? Now the load is W times x, that's the total UDL, and that will act at half of the distance. So this is W times x, and it will act at a distance x over 2 from this side. So W over x times x over 2. Which direction it acts? It will act anti-clockwise, so that's a negative sign. Now, as I say repeatedly, this equilibrium equation you can choose, you need to choose whether you will take clockwise moment positive or anti-clockwise moment positive. It doesn't matter what it is, but when it comes to the beam, the pair left hand side and right hand side makes the sign convention. So if one side is clockwise, other side has to be anti-clockwise. Same with the shear force. So the positive sign of the shear force and bending moment, what we have been using is as follows. So the positive shear force was left side going down, right side going up. Similarly, the moment we have used anti-clockwise on the left hand side is positive, and clockwise moment on the right hand side is positive, and the load coming downward is positive. So this is our sign convention that we have been using. So W times x is the total load times x over 2. X over 2 is the distance from here to there, so minus Wx times x over 2. So it is creating an anti-clockwise moment about that.
Firstly, what is y?
Y is the deflection. Y is when the beam deflects. So if you have got this beam, due to the load, let's say it deflects. So you have got some loads, the beam deflects in this way. So this is the deflected. So this is the deflected shape. So if you take x along that direction and y along direction, so that means if you come at a distance x, y is the deflection.
Also, where did you get the over 2 from? Can actually be clarified?
This one
No, throughout the entire equation, we start out with,
here.
yeah, WL m is equal to minus W.
So WL over 2 is the reaction force in the two sides. So the total load is WL. So the reaction force at each end would be, at each support would be WL over 2. Is that okay?
So that, yeah, so the bending moment across the distance x along B is given by the bending moment
Bending moment caused by this reaction force at the support is WL over 2 times x at this location. And bending moment caused by this little train of load is minus Wx times x over 2, because that is causing anti-clockwise moment. Is that okay?
Yep.
And then of course we have got mx, which is acting at a clockwise distance, direction. So plus mx. So these three are the moment producing forces at this location. So that would be equal to 0. So if you say what is mx? Mx would be minus WL over 2x plus Wx square over 2. So this comes from these expressions. Okay? So this comes from that expression. So we also know now, so we first step for this calculation of deflection is you find value of bending moment at an arbitrary distance x. So you take a distance x. Why do you do that? Because we are going to exploit this expressions of curvature, which is d2y dx2, to calculate deflections y, where y is the deflection. So this is the moment. So EI d2y dx2 is moment, or you can say d2y dx2 is w over EI x square over 2 minus Lx over 2. So that's the expressions relating to second derivative of deflections with respect to the known quantity of load, known quantity of E and I. So how do I find out this this y then? Now if you integrate it once, then you will get integration of d2y dx2 would give you dy dx. Now what is dy dx? Dy dx is the slope. So this is dy dx. Dy dx is the slope. And y is the deflection. Y is the deflection at a distance x. So if you integrate it once, then integration of x square would give you x cube over 3. Multiply that with 2 at the denominator, that gives you x cube over 6. Integration of Lx over 2, L over 2 is constant, length is constant. So integration of x dx gives you x square over 2. So x square over 2 times 2 in the denominator gives you x square over 4. Now of course then you add an integrating constant, which is a, which you don't know yet. So the slope of this beam, if it deflects under the load, would be this expression W over EI. So it will depend on the load. So if the load intensity is more, the slope at any point would be more as well. And it will also depend on the x, which means where you are calculating the slope, and also some integrating constant for which the values we do not know yet. Now if we are integrating it once more, we will get the deflection. So if we do that, if we integrate it once more, then I could get if I integrate it once more, then I'll get x cube over 6, x cube integration is x to the power 4 over 4, that gives you x to the power 4 over 24. And then x square integration is x cube over 3, that gives you Lx cube over 12. Integration of a is a constant, that would give you ax, and another integrating constant is b. Now, of course, we don't know these values of a and b. Now, we know few other things from which I can find out a and b. Because if I look at the beam now, at x started at this point. So, at x equal to 0, my deflection was 0, because I assumed the deflection would be something like this. But at a support, the deflection is 0. So, at x equal to 0, y equal to 0. That is my one known condition. And the second known condition is, if I go at x equal to L, which is the other support, my deflection is 0 as well, y is 0. So, I will use those two conditions to find out my a and b. So, at x equal to 0, y equal to 0 means no deflections over left hand support, and at x equal to L, y equal to 0 means no deflection on right hand support. So, with a bit of algebra, if we put y equal to 0 and put x equal to 0, that gives you b equal to 0. And if you put x equal to L and y equal to 0, you give a equal to this expression. Now, we can go back to these expressions here, put back values of a. So, you will get your expression of dy dx as this. So, this is your dy dx, or the slope. And similarly, deflection you will get values, expressions as that. So, this is y and this is dy dx. So, for any point on the beam, now you can, so you can draw these on in Excel or any other by varying the values of x in terms of the L. So, if L was 5 meter or 10 meter, so you vary x from 0 to 10 meter, and with these expressions then you can get it. Now, of course, at the mid span, you can, by symmetry, you can expect maximum deflection will occur. So, you put x is L over 2. If you do that, then you will get y max, which is at the midpoint is 5 W L to the power 4 by 384 di. And maximum magnitude of rotations or the slope will occur either end. So, maximum rotation or the slope is either here or that end. That is where the maximum rotations occur. So, you put x equal to 0 to get dy dx and x equal to L, and you will see they come up with the same magnitude, but different values, different signs. So, positive and negative slope. So, what did we do to get the deflection of a beam? So, we use this expression, moment is proportional to curvature. Curvature expressions we approximated from a scary looking curvature experiment. So, this is an exact expression. So, if we assume dy dx is small or slope is small, in other words deflection of the beam is small, then the slope would be small as well. So, the denominator can be approximated as 1. So, curvature is d2y dx2. So, we put that in here instead of curvature 1 over r, and then we find the first step is to find the moment expression at a distance x, at an arbitrary distance x. If I get that, then I put it back to this equation, that moment is ei d2y dx2, and then integrating it twice. Integrating it once, I will get the slope with an integrating constant. Integrating it twice, I will get the deflection. And of course, I will have some two unknown constant, which we can then find from my known conditions of deflection and rotation. So, if I know deflection at x equal to 0 is 0, x equal to L is 0, I will use those expressions in here, in this expression that I have got, and I will find a and b. And that will complete my expressions of deflection, expressions of rotations, and then once I plot it, I can find out what the maximum is and which point it would be maximum, etc. So, this is the steps or process that we use to calculate deflection of beam. Things would be a little bit complicated, but process is the same. So the process to summarize is as follows. First is, again, determine an expression for the bending moment distribution. So take a distance x and write down what is the distributions of bending, what is the value of moment at x. Now, x is important here because that we are treating moment as a variable across the beam here. And once we know that, then insert this expression of into moment curvature relationship and integrate it twice to get the deflection. And identify the beam's boundary condition from its support arrangements, and then that would give you the two unknown constants of integration. So this is the basic approach we will be doing. So we can do another problem which would be slightly different in terms of the boundary conditions. This is the third point would be different. But let's look at that. So it's a cantilever beam under uniformly distributed load. So again what we'll do is we'll take a section at a distance x. So x is starting from, so this is the origin, x starting this direction, y is downward. So we'll take a section x at this point here, for example. So if I draw the beam again, the part where we want to take a, so this is the part of the beam and this is the distance x. So this is the distance x, and where we have got the load as W per unit length, and as we have made a cut here, we will have a shear force and a bending moment. Shear force and a bending moment. Okay, let's say this is N. Now, of course, this was a fixed support, so the total load here would be, the reaction force would be the total load. Now, cantilever free end. Now, some of you made this mistake in the last problem, thought the beam was a simply supported one. Now, it seems that we haven't done enough problems with cantilever, which probably that we'll be doing in the next week, probably few more problems on the cantilever, because not all beams are simply supported, or not all boundary conditions should be like simply supported. It could be one of the common one, but cantilever is very common as well. So cantilever, this is the free end. All the support is in this point, in this left hand side, both support against displacement as well as the rotation. So as it is, the support is in this direction, is the vertical force would be the total load it would support, so that is W times L. So that would be for the whole beam, that's the support reaction. Will there be any support moment? So what do you think the support moment would be? So what do you think the support moment will be? Yeah, counterclockwise moment, but what is the value?
The value is going to be exactly the same as the bending moment caused by the
Not necessarily, because x could be anything. X could be half L over 2. So you don't expect the support moment to change. Support moment is for the whole beam. So what would be the support moment? Yes, so it's a total load times L over 2. So WL times L over 2. So that is WL square over 2. Yeah. So then the moment you can find out is WL square over 2 with a minus sign, minus WL times X, etc. You could do that. So the moment here in these expressions you could write as moment is clockwise here, so M. This moment is anti-clockwise, minus WL square over 2. This moment will create WL times X as a clockwise moment. So that would be plus WL times X, and this moment would be anti-clockwise, minus WX square over 2. So that equal to 0. So if you do that, then you get m is equal to that expression. Now this looks very neat. That is because in this case, the moment was calculated only about the right hand side, so that to ignore the necessity to know the support reaction. So how this could be done? Now let's quickly see that. So if you take only the free body diagram of the right hand side, if you do just the right hand side of the diagram, just the right hand side of the diagram. So if this is x, then that distance is L minus x. Okay. So what is the load? Load is W times L minus x. Now shear force is, so you have made a cut here, so the shear force would be vertically downward on the left hand side, and moment would be along that direction is the moment. So then moment is W times L minus x times L minus x over 2. So that is the equations in here. So that is looks very neat because we got rid of the trouble of calculating these reaction forces, support reaction forces and moments. But these two are exactly the similar. So here we have calculated this moment and that moment are exactly same, because in one section you have considered moment on the right hand side and moment on the left hand side. It's exactly the same. So either taking a free body diagram of the left hand side or the right hand side should give you the same moment, and you choose which one is more convenient. Now definitely in this case, doing the free body diagram of the right hand side would be easier, because you only need to calculate moment due to one set of load. So one set of load is W times L minus x. So this load, total load would be W times L minus x. That's the total load, and it will act at half the distance, which is L minus x over 2. So your moment is W times L minus x times L minus x over 2. So that gives you half W L minus x square. So first step is done. Determine an expressions for the bending moment distribution. So the first step is done. So you have taken a distance x and find out bending moment would be what at that section. So bending moment in terms of x. So if you vary x, you will find the bending moment. So let's check whether we get that. Put x equal to 0, which is at this point of the support. If you put x equal to 0, you get moment is half W L square. So which is right? That's the support moment. So moment at the support is W L square over 2 if you put x equal to 0. Try putting x equal to L, which is the free end. If you put x equal to L, moment is 0. That means free end moment is 0, which is also correct. So this expression is right. Now the second step is insert this in the moment curvature relationship and integrate twice. So what it means is that EI d2i dx2 is m. So you put it in there. So then you put d2i dx2 is this expression. Expand that bit so that you get L minus x whole square is these expressions. Then integrate it once. You get L square integration is L square x square L x square integration x cube over 3 plus a integrating constant. Integrating another time, you get all this expression. A integration is ax plus ax, and then another integrating constant b. So you integrate it twice. So this is your expressions with some unknown values a and b. You find these from the known conditions of your beam. So what are the known conditions? So the two known conditions for this beam are that at x equal to 0, which is at this point, y equal to 0. So that is one known conditions. And the second known conditions at this point is the slope is 0. So at x equal to 0, dy dx equal to 0. So you use those expressions, dy dx equal to 0 at x equal to 0 will give you a0. And we know also at the support there is no deflection, so y equal to 0 at x equal to 0. So if you do that and with a bit of simplifications, you get expressions of slope is this, expressions of deflection as that. And you can find out the maximum deflection would be occurring at z equal to, not z, x equal to L. So at x equal to L would be the maximum deflection, so which is EO WL to the power 4 over 8 EI. So, so that's it really in terms of the process and the methods. So these 4 steps. So determine the expressions for bending moment at any distance. Put as EI d2y dx2 is the bending moment. So the first step you calculate moment, second step you equate that to the moment and then integrate twice, and third step you identify the beam's conditions to get integrating constants A and B, that will get from third step, and finally this third and fourth step primarily, as we are saying, is this to determine the unknown conditions. So this is nothing more complicated than, as you could see, calculating the bending moment expressions, and that is probably the most difficult bit, and the others are fairly straightforward. Only thing is, what will happen is, calculating this expression of bending moment would be difficult if for a simple case like this, where you have got a point load somewhere in the middle, or you have got a point load and an UDL. Then expression of bending moment will be different if you take a section here. If you take a section here, then bending moment would be W over 2 times X, and bending moment here could be different, W over 2 times X minus W times L minus X minus L over 2, etc. So these sort of things we will see how we can handle that and various other. So we will introduce one more concept, and that I promise would be the last concept wise we will be using. So read the notes before Thursday. It's something called Macaulay brackets. So this is in mathematical terms something called unit step function. Something also in mathematical terms it's called unit step function. So this is the only thing which you, if you haven't done with maths yet, this is the only thing that we will be using, and that's it. So I am not going to use any more concept, and then we'll look at examples and solve problems for the next 2 weeks. Okay, see you on Thursday, but please read the rest of the notes for this part before Thursday. Okay? And I have uploaded your, if you go into here, you'll find the solution of quizzes. Oh, that quiz 3 would be, I'll be uploading today as well. Okay. Is Young's modulus of elasticity.
So like for the question here, you're saying like if the dy over dx is small, what if it's big?
Then you have to solve this one, which is scary. You don't expect that to do, you use a computer to do that.
Yeah. Is there a ratio whether?
So typically about 1 in 10. So if it is more than that, then
That is big.
then that's big.
Okay.
Then you cannot expect that to use that. Hi, you're okay? Not bad.
I'd like to know the next online test, it will be next week.
Next week, yeah.
So on 17th December we don't have test.
No. No, on the last week there will be no test. Yeah.
About the so in the test,
Yeah.
on one question, so I put the signs in by accident.
Send me an email. I'll update that mark.
Okay.
So I'm not going to penalize for the signs because that was not possible to do that in Blackboard. Yeah, I'm not going to penalize for that. Yeah, send me an email.
Question, in a problem like this, can we approach first from the left and then from the right, or no? In this problem can we first approach from the left and up till here, and then from the right?
Yeah, you can. You can. Absolutely. Whatever makes the calculation easier, people tend to do that. So if the coming from both ways is easier, do that. But make sure that you are using appropriate signs for coming from left or right.
For the deflection,
Yeah.
like after we find, are we supposed to find an expression for dy dx, or we just integrate that set? We only find an expression for y.
Whatever is required. If they ask for deflection, then you have to integrate it twice. If they ask for rotation as well,
So what's rotation? I didn't understand.
rotation is a slope. So if you have a beam deflect like this, then this is the slope. So hold it back out of it. So this is the slope. And that's the rotation. You know, if this chart bends up, the atom have a different slope. That's rotation.
Oh, the dy dx bit.
dy dx, exactly. For which one? So for which part? First problem or the second problem? Second problem. So second problem is, yeah. So second problem is we take equilibrium of the right. Let's see how the other. So if I take a moment at this, so what is the total load? Total load is W times the length of load plus, right? So W times, let's say this load is 5 meters. So W times 5 meters is the total load. Where that will act, it will be acting as the middle of this load strength. So that will be 5 meters. So then I take a moment of that load, which is W times 5 meters.